Hello, calculus people. I'm going to try to make a video of the notes we would have taken in class today. I will try not to make it super long, but I will try to make it very useful. So I apologize to you if it doesn't feel that way. What we're doing in section 8.1 is looking at accumulation and net change. What you want to remember about accumulation is basically anytime you integrate a function, you're accumulating things. Some important things to know, if you look over here at the objectives, displacement is the integral of velocity. Total distance is the integral of the absolute value of the velocity. We can find net change from graphs and from tables that have the rate of change. So if you look at example 1, it kind of helps us get started. So what we have in example 1 is a function, which is a velocity function, and it looks like it's velocity in centimeters per second. So we're talking about a particle that's moving along a horizontal axis, so the particle is moving back and forth. If we look at a graph of the function, it gives us a pretty good idea of the behavior of the function. So notice that the velocity starts out down here underneath of the x-axis. So the velocity starts out as negative. It's 0 right about here, and then it becomes positive. Okay? In later examples, we'll use our algebra to solve equations to find out where velocity is equal to 0. So if we did that with this one, there'd be some pretty tricky algebra. So what we would do, though, would be to set t squared minus 8 over t plus 1 squared equal to 0, and then solve for t. If you look at the graph, we can kind of estimate that that point is about 1.25. Remember that this interval starts at 0, and according to the information given to us, we're going to go up to 5, right? So we know from the graph that the velocity is negative between 0 and 1.25. If we didn't have the graph, we could put a number between 0 and 1.25, take something from in here, and put it into our velocity function, and that would tell us that everything in that interval is negative. We can do the same thing for the interval between 1.25 and 5, but we find out that that's positive. And so what we want to say then is that the particle starts out moving to the left. It has an initial velocity of 8 centimeters per second. I know that because if I put 0 in here, v of 0 equals 0 squared minus 8 over 0 plus 1 squared, which is 8. So my particle starts out moving left with a velocity of, well, actually this is equal to negative 8. So it's moving left with a velocity of negative 8 centimeters per second. At about 1.25 seconds, it slows and then stops. And then it moves right from 1.25 seconds to 5. When velocity is constant, you think about that. If you're traveling 60 miles per hour for 3 hours, the distance that you've moved is just equal to your velocity times your time. But if velocity is not constant, we want to find what is our ending position minus our our ending position minus our beginning position, which is our displacement from the beginning time to the ending time. In order to find that value of displacement, that's equal to the integral. So if we wanted to know the displacement of the object up here, that would be the integral from 0 to 5 of t squared minus 8 over t plus 1 squared, right? So we would take that integral, and then we would find, when we find that, we would take the integral. Remember that sometimes this is referred to as little f of x, and so the integral of that is big F of x. We would take f of 5 minus f of 0, and that would tell us the displacement of our object.